In this video, I want to give a short history of mathematical truth. Well, I suppose mathematical truth itself may not have a history, but what has a history is our thinking about mathematical truth. How do people, mathematicians maybe, philosophers maybe, think about the nature of mathematical truths? What are mathematical truths about? How do we know them? What makes them true? The reason to talk about that in a series of videos, which is at the moment focusing on a priori knowledge, is that mathematics has always been the quintessential, prototypical example of real, substantive and interesting a priori knowledge. If philosophers have been asked, well, give me some example of things that we know without an appeal to experience, mathematics has usually been at the forefront of their minds. So already in the ancient Greek world, the status of mathematics as this sophisticated body of knowledge that didn't need experience seems to have inspired people like Plato to believe that, the best knowledge about the world is knowledge that doesn't need sensory experience for its justification. And you can go like 2000 years forward in time, pick up a book like Spinoza's Ethics and see that Spinoza believes that in order to really do metaphysics well, what we have to do is emulate the method of mathematics. Okay, so it's going to be useful for us to look at how our thinking about mathematical truth has changed and what kind of problems we run into as we try to think through that issue. So, what I'm going to do is I'm going to first talk about the most classic model of thinking about the nature of mathematics and mathematical truth, a model that we can find already in the ancient Greek mathematician Euclid, and which remained the dominant model, the dominant way of thinking about mathematics until well into the 19th century. And so, for instance, it is the way of thinking about mathematics that we recognize in Spinoza's Ethics. So here's the idea. What Euclid does when he sets out his theory of geometry is he gives us certain axioms, so basic axioms, which are supposed to be, on the one hand, obviously true, right? Obviously true. If you just think about them, you can see that they're true. So, for instance, one of Euclid's axioms tells us that if we have 2 points, a line can be drawn through both of them. Right? Well, that seems obviously true. If you have 2 points, a line can be drawn through both of them. Yeah, well, that seems right. So the axioms on the one hand are supposed to be intuitively true or obviously true, or we have rational insight into their truth, something like that. And on the other hand, the axioms are also supposed to form a basis of everything else that we find out in mathematics. So what mathematicians do is they reason on the basis of the axioms, right? Assuming the axioms, we can use logic to prove further theorems. And that is exactly the shape that Euclid's geometry has. We have some axioms, and then Euclid starts proving theorems on the basis of those axioms. And the idea is that if you do this carefully, then if the axioms are true, all the conclusions, all the theorems have to be true as well. And if the axioms are obviously true, well, that means that, everything that we end up with, all our conclusions, are going to be true. And so that's, for instance, what Spinoza wants to do in the Ethics. The axioms are supposed to be obviously true, and then through cold logic, we get to theorems, new insights that are also true, because they are drawn from the axioms. So that is one important part of the, let's say, Euclidean way of thinking about mathematics. But another ingredient has to be added, and that is that these axioms are supposed to be true about the world. Right? When Euclid talks about geometry, he is not thinking about some completely abstract mathematical thing that has nothing to do with reality. He is thinking about space, right? The space that we live in. The axioms, such as between every 2 points you can draw a line, are supposed to be true about space, right? This space, the very space that we live in, the very space that science is also investigating. And so what Euclidean mathematics gives us is the idea of intuitively true axioms that form the basis of a science that is about the world. Okay, so that's important. Self-evident axioms about the world. Now, here are some good things about this view of mathematics. It explains both why mathematics gives us certainty, right? It gives us certainty because we start from these self-evident axioms and we do only logical reasoning that is going to take us from truths to truths. And it explains why mathematics is useful, right? Because it's about space. I mean, what could be more useful as a basis of our scientific understanding of the world than a theory of the space in which things happen? And maybe we can use other parts of mathematics, maybe counting, to talk about time, right? And so we see that mathematics can be the basis of our scientific understanding of the world. So, what it does, it explains the certainty and the usefulness of mathematics, where by usefulness I mean usefulness for science and understanding the world. However, there's also a big problem here, a problem that is both epistemological and metaphysical. And the problem is, well, how can facts about the world be evident through rational insight alone? Right? If these mathematical axioms are true about the world, why don't I need to look at the world to see whether they are true? Right? How is it that merely by thinking I can see that they are true, that they couldn't maybe be false even, they are necessarily true? How is that possible? And in order to have a good story about mathematics, we have to give an answer to that. And some of the answers are going to jeopardize certain elements of this Euclidean picture, and other answers are maybe going to have, some trouble of their own, some problems of their own. So, I would say essentially, there are four possible solutions to this conundrum, right? How can we have rational insight into something that's, a fact about the world? Well, one option, the option that we're going to be seeing people taking in the 19th century, is to deny this connection to the world. It is to say, look, mathematical theories are not really primarily about the world. And we'll get back to that, right? I'm going to look at the other three options first, but we'll get back to this one because it is the absolutely standard move to make nowadays. Okay, here's the second thing we could do. We could say, well, look, maybe these mathematical axioms aren't self-evident. Maybe you need more than rational insight. Maybe they are actually empirical. So that's possible, right? One of the things we can do is we can say, look, mathematics maybe really is an empirical science. What we have to do is we have to, jot down a lot of points and check whether we can make lines between them. Maybe. Doesn't sound very likely, but there have been empiricist philosophers who have tried to do this, right? To claim that mathematics is actually a science, an empirical science. So Hume, for instance, is somebody who makes some suggestions in this direction. And Hume himself shows that it has some weird consequences. So, for instance, mathematicians can make numbers, you use numbers as small as they want, right? I mean, if you have a line in mathematics, you can always take a line that's twice as small and a line that's twice as small as that and a line that's twice as small as that and so on. And what Hume is going to say is, he's going to say, look, if you check out what the world looks like, you're not going to find this infinite divisibility, right? There's a smallest thing that you could possibly see. And so mathematics is actually not quite right? There's something wrong. Maybe the true mathematics would be one that uses smallest elements, which somehow have something to do with the smallest elements that we can perceive or that we can find in our physical theories of the world. Well, one thing we can say about such an empiricist project is that it would really change mathematics into something that currently it is not. So it's quite revisionary. Okay, I'm going to set aside this sort of empiricist move, like interpreting mathematics as an empirical science. I'm going to put that aside. Okay, here's a third possibility, and it's been very popular in, ever since the ancient Greeks, so it's not so popular nowadays. The idea would be that there's, in one way or another, a kind of pre-established harmony between our minds and the world. Right? If the world has been made through these mathematical ideas, and if these mathematical ideas have also been implanted in our minds, then the fact that rational insight alone gives us insight into the nature of the world isn't so strange. Right? So this is basically the Platonic story, and it's a story that we're going to find in many, many, many different ways throughout the centuries. Right? It's the idea, for instance, that God has created the world with a certain order, right? At least part of that is going to be a mathematical order, and that God has created our minds in such a way that we can understand that order, right? That we can already find that order in our minds. Okay, so maybe that works, right? That seems to give an explanation, some kind of explanation, for why rational insight into mathematics can also at the same time be rational insight into the world. But of course we need a pretty strong metaphysical theory for this. Right? We need something or someone or some principle or whatever that ensures that our minds and the world work in the same way. And of course that raises some metaphysical questions like what is that principle or being or whatever it is, and also some epistemological questions. Right? How do we know that whatever ideas were implanted in us are the ideas that are also true of the world? Right? And these are questions that are going to, for instance, exercise somebody like Descartes, who worries, at least some of the time, that maybe, my mathematical insights, couldn't they be false, right? Couldn't they be wrong? And of course, Descartes is going to bring in some metaphysical story about the goodness of God to argue that doesn't seem likely, that doesn't seem to be the way things could be. But there are serious epistemological problems here. Alright, fourth option, not that popular, but I want to mention it. You could have the idea that, well, maybe these mathematical structures are somehow in our mind, but because they're in our mind, they're also in the world. Right? So this is not the empiricist who says, well, the structures are in the world and we learn them by investigating the world. It's not the pre-established harmony which says, well, the same structures are put into the mind and the world. No, here the structures would be in the mind, and because they're in the mind, we can also find them in the world. That is, one way at least of understanding Kant's transcendental idealism. When Kant tells us that space and time are the forms of intuition, and therefore the formal aspects of all appearances, that's the kind of story that he's telling. It can't be surprising or weird or uncertain whether mathematics works when we investigate nature for Kant, because mathematics is about the structure of our minds, well, the structure of our intuitions, the structure of how we can sense, and therefore necessarily it's also going to be the structure of the sensible world. Okay. Transcendental idealism too, comes with a lot of metaphysical questions. I mean, what is that world? How do we know that mind and world have this relation? And so on. So, options 2, 3, and 4, right? The empiricist option, the pre-established harmony option, and the transcendental idealism option are basically the options that are on the table if you want mathematics to be about the world. Now, in the 19th century and then in the 20th century, some things happen that change the minds of both mathematicians and philosophers about the relation between mathematics and world. So, let me give you the two most important things that happen. The first most important thing that happens is that mathematicians find out that actually there are other mathematical theories that you can develop in just the same way as the standard mathematical theories. So take geometry. Like Euclidean geometry has 5 axioms, and we can develop an entire geometry based on those axioms. But one of those axioms had been giving people a little bit of trouble or doubt, like forever. It's what Euclid tells us is that if you have a line and you have a point that is not on that line, then through that point, exactly one line can be drawn that never crosses the first line. Right? It's called the parallels postulate, because basically it says if you have a line and you've got a point that's not on that line, there's exactly one parallel that you can draw. Okay, and it's very important. You can't do a lot of mathematical proofs, a lot of geometrical proofs without that postulate. What people find out in the 19th century is that actually you can take away that postulate and put in another postulate. You can put in the postulate that there are infinitely many lines that are parallel. You can put in the postulate that there are no lines that are parallel. And in both cases, you can do mathematics, right? You can prove theorems. It works. It's interesting. And mathematicians actually like to investigate this. Okay, so that's a little bit worrisome, right? It's a little bit worrisome maybe that there seems to be options open for mathematicians, and you don't run in trouble doing mathematics by taking one of these other options, by taking alternative axioms. Okay, but we might still think that, that's nice, that's maybe a game that mathematicians can play, but the Euclidean axioms are the ones that are obviously true, and so they must be true of the world. Okay, here's the second thing that happens. In the 20th century, physicists changed their ideas about space. And in particular, when Einstein comes up with the general theory of relativity, part of what the general theory of relativity says is that if there are masses in the world, then space is not Euclidean. So these alternative axioms actually turn out to be the axioms that are most useful to physics. And physics presumably describes the world. And so suddenly it turns out that maybe those Euclidean axioms aren't really the axioms that are true. Or at least whether they are true or not, that's an open question, and it's an empirical question, and one that we can investigate and even apparently be wrong about for thousands of years. So, these developments make the old story, the Euclidean story, where you say there are self-evident axioms and they're true about the world, very hard to hold on to. Because it seems that, the axioms that people thought were self-evident don't seem to be true about the world, or at least it's very much an open question whether they are, right? So how to deal with that? Well, here's the, overwhelming consensus nowadays. The overwhelming consensus nowadays is that mathematicians investigate what we call formal systems, right? Yes, they just choose a bunch of axioms that are interesting to investigate. And yes, they can choose different bunches of axioms depending on what they're interested in investigating. So yeah, you can do Euclidean geometry, you can do all kinds of other geometry, right? Things can get pretty wild. And then, if we want to apply mathematics to the world, it's just an empirical question whether any of these systems are going to be right for the phenomenon that you want to investigate and describe. So, if you're talking about space, the knowledge of the mathematicians might be a priori, right? The knowledge of the mathematicians inside their formal system is a priori. Yes, in the Euclidean system, it's a priori true that, all these theorems are true. But that doesn't tell us anything about the world. If we want to know whether any of that stuff is true about the world, we need empirical investigation, right? And so this is the way that most mathematicians, most physicists, most philosophers nowadays think about it. Mathematical truth might be a priori, probably is a priori, but it's not about the world. If we want to apply it to the world, we need to connect it to the world through empirical investigation. And that means that geometrical knowledge inside a formal mathematical system is a priori. But geometrical knowledge in the world, if I claim that in reality the three angles of a triangle are 180 degrees together, well, that's an empirical claim. And it's one that actually, if general relativity is true, might well turn out to be false. So, this, by the way, does leave us with a problem. It leaves us with the problem of why mathematics is so incredibly useful in investigating the world. Because it is. Right? I mean, we can't do modern physical science without mathematics. And if mathematics is just about formal systems, and if those formal systems have no intrinsic connection to reality, why does mathematics work so well in physics? That's not a question I'm going to try to answer here, but it's good to know that this question is there and that people are worried about it and are trying to answer it. For us, maybe more importantly, it generates a question about the epistemical relevance of mathematical knowledge. Right? For a long, long time in philosophy, if you wanted to show, well, there is substantial a priori knowledge about the world, you could point at mathematics. And now it seems that you can't do that. Right? You can point at mathematics to claim that there's substantial a priori knowledge, but you can't really point at mathematics to say that there's substantial a priori knowledge about the world. Right? It seems to be knowledge about formal systems. Systems that we ourselves create by choosing a bunch of axioms. And that seems to be philosophically a lot less pregnant. Right? If you want to say, oh, there's something wrong with empiricism because we have all this a priori knowledge, well, that's a much stronger move if you mean a priori knowledge about the world than if you mean a priori knowledge about things that we have thought up ourselves but which don't necessarily have anything to do with the world. Okay. Well, that's something we'll be talking about again in the next video. But when we want to understand how philosophers think about the a priori, we have to understand how in history mathematics has sort of fallen from the lofty position of a priori knowledge about the world to, yeah, sure, a priori knowledge, but if you want to apply it to the world, you're probably going to need observations.